Hello everyone, this is Sudarshan.
This is Umaeshwar.
Today we will be giving a presentation on a course project, Face Identification using mmWave radars. So let's move ahead. Let's set the stage for the project. So what is face recognition? Anything that has to do with identifying human faces in general. Now there are subdivisions in face recognition as well. The first is face classification or face identification. This involves a one-to-many mapping. For example, we can take a person's image and classify it as one among many people's faces. The second is face verification or face authentication. This involves one-to-one mapping. Here, the answer is a simple yes or no. For example, is this person in the image the same one shown on the other image? Yes or no. So now let's move on to explain the project a little more in detail. We will be using a face recognition based technique to develop biometric authentication. In specific, we will be relying on the classification technique. This must adjust to minor changes in face appearances. Also, the main data will be obtained from 60 GHz millimeter wave sensors. So there will be two arrays of sensors to transmit and receive infrared rays from a face, and this can estimate angle and depth of facial structure. So now let's get to how the data set for the project looks like. So there are 32 transmitter and 32 receiver antennas. So that corresponds to 1024 values. And we have something called as taps. A tap is basically a set of 1024 readings that was mentioned. Now there will be 8 such taps per person. So that corresponds to 8192 values. There will be 200 measurements for one person for each depth and angle. And there will be 7 combinations of depth and angle. Hence, every person will have 1400 data points or images or samples. Now we have a total of 206 people in the current database, and the subjects include men and women at variable ages with or without classes and some having pairs. Overall, the general structure of dataset is that there are 22 files with roughly 9 to 10 people per file contained. Now let's move on ahead to the pre-processing part. So first, we obtain from the cross-correlated values of the sensor readings the magnitude and phase information separately. Next, we convert it into image-like format of size 256 cross 32 as shown in the slide. This aids in better visualization. Now we can see the peculiarities of each type of data. For example, the magnitude information is stored in few tabs, whereas the phase information seems distributed across all tabs. So with this in mind, I'll hand over to Umesh to elaborate more about the task at hand.
Thank you, Sudarshan. Now that we have seen more details about the data set, let's have a more focused approach. What is our task and how are we going to achieve it? This is going to be our discussion. Now, given a face sample, we need to identify which person it corresponds to. In one word, we are going to do classification. And for any classification task, it is important to choose the right model. So let us begin by understanding that first. The entire data set consists of 206 persons whose faces are mapped in 7 different configurations. Now, each configuration has 200 samples. If you calculate, this comes out to be around 290,000 samples. It makes sense to use a deep network for this dataset because of the sheer size and complexity involved. A dense deep network has many parameters to train, which is not what we ideally want. So instead, we go for a model which uses CNNs to reduce the computation cost. We chose GoogleNet, a widely accepted architecture, because it is robust and can detect very complex features. Now, this is what GoogleNet looks like. There are many layers and there are multiple 2D convolution and Maxwell operations that are applied. Now, don't be scared by the size of this model. You can see that there are some repeating units, like some repeating, networks inside this thing. So these are called inception modules, and these are what make GoogleNet very special. Let's take a look at one such module. Now this is an example of an inception module. You can see that the input of the previous layer is being given as input to 4 different operations: a 1 by 1 convolution, a 3 by 3 convolution, a 5 by 5 convolution, and a max pooling layer. Now the outputs of these layers are concatenated and passed on to the next layer. Inception modules allow the network to learn from more features by giving the freedom of choosing features to the next layer. Though this is very expensive, it can improve the model performance by leaps and bounds. I hope this gives you an idea about how powerful this model is. Now, to get to the elephant in the room, we know how long it takes to run a huge model on a large data set. Since there can be redundant measurements in our data, we can randomly take a fraction of the samples. That is, if we have 200 samples per configuration, we can trim the data, say by 5, so that there are 40 samples per configuration. So data trimming is an essential part of our experiments, which we list out now. As you can see here, we did the experiments in 3 settings. 1, a trimmed single file of data. 2nd, an untrimmed version of the same file. And the 3rd, a trimmed version of the entire data set. Under each header, we broadly did the following experiments. Using individual tabs of magnitude or phase information, using all 8 tabs of magnitude or phase information, and combining both magnitude and phase information by concatenation. The only exception to this is in the 3rd setting. In single phase experiments, we took only tabs 3, 4, and 5 for reasons that will be explained in a few minutes. This begs the question, how are single file and all file experiments different? So, in this table, you can see all the details of the model we employ. So the only difference in single file and all files is the number of classes we are concerned with. For single file, we train with 9 persons instead of taking all 206. So this will help us in checking the efficiency of our model. Now, let's take a look at the results of our model. Before we begin, please be aware that the next few slides will be full of numbers and plots. And in the interest of time, I can only point out what's important. If you'd like to take a better look, please feel free to pause the video at that point. And yes, it might be a little bit boring, so please bear with me also. So setting 1, trim dataset from a single file. Remember that it has data of only 9 persons. The first experiment is magnitude 8 tabs, of which we got a test accuracy of 96.43%. So here you can see the accuracy and loss plots, and they converge fairly easily. Now we'll move on to magnitude single tab, and the results are compiled in this table. So here you can see that tabs 3 and 4 give the best test accuracy, and these are the corresponding accuracy and loss plots for magnitude single tab. One thing to notice here is tabs 1 to 4 are on the left side and tabs 5 to 8 are on the right side, and they are ordered from top to bottom. So please don't confuse yourself there. Now we'll move on to phase 8 tabs, where we got a test accuracy of 87.7%. So here you can see that the accuracy is slightly less than what we got for magnitude 8 tabs. Next, we do an experiment with phase single tab. And again, like in the case of magnitude, tabs 3 and 4 perform considerably better than the others. And in this case, tab 4 performs better than tab 3. So these are the corresponding accuracy and loss plots for phase single tab. Finally, when we concatenated both magnitude and phase to get 16 tabs, the test accuracy is 89.68%. And these are the corresponding accuracy and loss plots. Notice that the test accuracy is between that of magnitude 8 tabs and phase 8 tabs. This is a trend which will be observed later as well. Setting 2, untrimmed data from a single file. So this is the first experiment in that magnitude 8 tabs, in which we got a test accuracy of 99.92%. Just look at the accuracy and loss plots. It's like, it converges so fast, both are almost looking same only. Now we'll move on to magnitude single tab. So here again, as in the case of setting 1, so tab 3 and 4, they perform considerably better. And the thing to remark is tab 4 has 100% test accuracy. And these are their corresponding accuracy and loss plots. Now we'll move on to phase 8 tabs, where we got a test accuracy of 87.38%. As in the case of magnitude, so the convergence happens pretty quickly, and you can see that the accuracy is also very high. But one thing to note is again, the phase 8 taps accuracy is less than that of magnitude 8 taps. Next experiment, phase single tap. So here again, we can see that taps 3 and 4 perform considerably better. And again, tap 4 is performing better than tap 3. Same trend as last time. So tap 3 and 4, the test accuracies are less than those of magnitude single tap. So these are their corresponding accuracy and loss plots. Now, when we concatenated magnitude and phase to give 16 taps, we got a test accuracy of 95.87%, which is again between that of magnitude 8 taps and phase 8 taps. Okay, so this concludes the result on the single file. Whether the trends extend to all 206 persons or not has to be seen. So to explain this, let me call back Sudarshan. Once again, thank you for your time.
Yeah, thank you, Umesh, for explaining the part so beautifully. Now, before we move on ahead, I'd like to remind you a couple of things. So, from the previous set of experiments, we have understood two main things. First, tabs 3 and 4 are of the main interest. And second, the phase results in general show a dip in accuracy compared to the magnitude results. Keep that in mind as we go to our next section, dataset trimmed for all files. So there will be a lot of sample points for us to test on. So we have to see how this extra data and the extra number of people are going to affect our experiments. Let's move ahead. So the first experiment, magnitude 8 taps, has a test accuracy of 98.05%. So far so good, as we have got a very good convergence rate as seen in the loss plot. Now let's continue our experiments with magnitude single tap. So here as well, we tested out on taps 3, 4 and 5 and got a pretty good test accuracy of 86.51, 92.66 and 88.79%. So this again shows that there isn't much of a change from whatever observations we made for the single file case. So let's take a look at the accuracy and loss plots. So here you can take a look at how they're converging. So now let's move ahead to the next set of experiments. Here is where we see a slight deviation. The first thing is that this is for phase 8 taps. The test accuracy is 74.99%, which is comparatively lesser as to the previous set of experiments. So we have to keep this in mind as we move ahead. These are the accuracy and loss plots. Let's see if this extends to any other experiments as well. So we'll move on to the phase single tap. Again, tabs 3, 4 and 5 are the best performing tabs. So that particular observation holds good here. But the test accuracies have clearly taken a hit compared to the previous experiments. So here are the plots. Interesting thing to note here is that the convergence is pretty much the same until a fixed number of epochs. After that, there is a slight wide deviation between the validation and training, both loss and accuracy. So let's move on to the last experiment where we check on the concatenated magnitude and phase 16 taps. Here the test accuracy is 76%. Again, not a bad accuracy, but compared to the previous experiments, it is pretty less. And the convergence is happening well, but there is a deviation between the training and validation accuracy and loss. So let's just summarize these results that were displayed by taking a look at its table. So we have filled all the results in this table, and as you can see, all the results seem pretty good, and there are only 3 results that are of particular interest. The last column, dataset trimmed all files, wherever there were phase data involved, we have seen a slight dip in the accuracy. So why is it so? We have to analyze it in the coming slides. Let's move on to the observation section. So from the table and from our simulations, you can see that magnitude training gives the best results irrespective of how many of our files or whatever experiment it is. And phase is yielding less accuracy than magnitude, and this translates to the concatenated input as well, as we are taking both phase and magnitude. So there could be a possible number of reasons for this. First, is that hyperparameters may not be tuned properly. So to rectify and to take a look at this problem, we did test it out on a variety of hyperparameters, and we varied it like around 10 or 15 times. But we are seeing that the hyperparameters do not make a difference in the overall output. So the second step that we can take is changing the optimizer for the last set of experiments, just for the phase training. The final and the last measure that we can take is that we can combine the magnitude and phase information in a better way to yield better results. Also, note that this effect of decreased accuracy for phase is more pronounced in the third setting. So the last observation is, of course, tabs 3 and 4 seem to be the main tabs of interest in both phase and magnitude, and this seems consistent across all experiments. So let's move on to the conclusion section. Uh, First conclusion is that deep learning approaches are yielding good results for face recognition. Accuracies are more than 90% in most of the cases, and any future work is going to be promising. The second conclusion is to improve results, we need and must do better hyperparameter tuning. We have observed that even in our set of experiments that without tuning, the results tend to vary very wildly. So let's move on to the next section. We'll discuss a few potential future work that can be included with the current project. First is to try out other architectures like ZFNet, which can reduce computational cost. So we have used GoogleNet here, and this might not be the smallest network around. So we can use smaller networks to reduce computational cost. The second and the more coding aspect that we can work on is to integrate the current deep learning program with a database system like MySQL to reduce time to load the data. So currently what's happening is that we are taking a significant amount of time to load the large data into the file and then train on it. So we want to reduce that time every time we train. So the third potential work is to design a phase verification system based on the FaceNet paper. And the last but not the least, we can compile results from both these classification and verification models to complete the overall big picture, that is the face recognition system. So let's move on. The reference material that was used for this particular project includes two research papers. The first one, face verification using MM-wave radar sensor, is sort of related to the dataset aspect, whereas the second paper, going deeper with convolutions, which is a famous paper, is the basis for our conceptual aspects. Now we'll move on to the acknowledgement section. We are very grateful to Dr. Ramakrishna Gothi sir for giving us an opportunity to extend our ongoing project even further. Also, we have special thanks for Ms. Ravi Vaishnavi, our PhD student at IIT Tirupati, and also our TA of our MLIP course, for helping us to get access to GPUs on campus, which significantly reduce the training time. So let's move on. Thank you, and we hope that you learned something out of the presentation, and also thanks for listening to all those plots and the explanation with patience.